Okay, just a couple of comments, two or three actually. One, I sent a reminder to you, just don't forget your next exam, it will close today at 10 p.m. So give yourself plenty of time covering chapters 4, 5, and 6. Keep it simple as far as the questions. Don't make it more complicated than it should be. We're not trying to confuse you. Okay. That's point number one. Point number two is this. I've been reading a lot of the inputs as far as the activities, and you're writing an explanation about some trend or so forth. I'm having a bit of a challenge when I read some of these things. Okay, so I'm going to give you some advice that was given to me 100 years ago by my graduate advisor. He stated this, and I kept that advice throughout my career. And he said, when you write something, obviously write it in complete sentences, and to the point. It's not necessary to add additional other stuff that has nothing to do with the topic at hand. But write it in a manner so that if you, for whatever reason, need to read it again 5, 10 years from now, you're able to understand what you wrote. More importantly, is the majority of you are going into professional fields, and you'll be asked to write something, write reports, write something, either for a presentation or any number of things. I don't want to pick on nurses, but half of you are nursing. You have to write reports about your patient for the other shift, and you want to make sure you are specific enough and correct enough to write something so the next person can understand what's going on. Engineers, same scenario. I've worked with many engineers in my professional career, and you got to write something, write it in a manner that somebody that will understand it. Okay, so take a few minutes before you submit something, especially during the exam, that you got to write to explain something, write something about it. Make sure it's in complete sentences so I can understand what you're trying to say. Okay. All right. So enough of that. Where were we? We were on chapter 7. Let me pull 7 up. And my record show we stopped on slide 12. Okay. And so what we're talking about here is about the chemical bond. Now, prior to this, we talked about the covalent bond. And there's 2 types of bonds now, okay? 2 types of bonds. The first bond is an ionic bond, and that's very straightforward as to what constitutes an ionic bond. And that is a combination between a metal and a non-metal, okay? So we have to identify what the metals are and what the non-metals are. Now, in that particular type of bond, it is not, quote, a true bond. We call it a bond, but it's not a true bond. Nevertheless, we call it ionic bond because in that scenario, we have a full-fledged positive charge and the negative charge very analogous to two magnets coming together and attaching themselves. That's the attraction. That is the bond with respect to ionic bonds. Covalent bonds don't do that. Ionic bonds, when we put them in water, they dissociate completely into the specific ions. Covalent bonds do not do that. They don't break up. There's only one exception, but we'll get to that when the time comes. They actually share electrons to form a physical bond between 2 different atoms, okay, or the same atoms, because we can have a covalent bond between the same atom or different atom as long as they're both non-metals, okay? So we can have single bonds, triple bonds, and double bonds. Well, single, double, and triple bonds. And how we designate that is, let me show you very quickly. You'll see it written numerous times. And let me just take this. So for example, if I have a carbon and a carbon bonded together. And so I draw this line here that represents 2 electrons. And that is one line, 2 electrons, which is a single bond. Okay. When I draw two lines, that represents 2 bonds, which is a double bond. Okay. And so there's 2 electrons per line. There are 4 electrons. And then we have the triple bond, where that is represented by 3 lines. And I'm just picking 2 carbons. Okay. It could be a carbon and a nitrogen, for example. But that is a triple bond with each line representing an electron, 2 electrons. All right. So with that in mind, let's go back to that slide. So 2 electrons, 1 single bond. Double bond, 4 electrons, 2 pairs. And a triple bond, a total of 6 electrons, 3 pairs. Okay. Now, with respect to the length, there's a bond length here. And in the strength, the single bonds relative to single, double, triple are the longest and the weakest. Whereas triple bonds tend to be a lot shorter, and they carry a lot more punch. They're a lot more, have a lot more energy. For example, acetylene is a triple bond hydrocarbon. Acetylene in combination with oxygen is utilized to cut metal. There's so much heat, so much energy is involved in that triple bond, enough to be able to create enough heat to burn and cut metal. Compared to a single bond, which could be an analogous to with respect to hydrocarbons like butane. The gas, butane and propane are all single bonds. They give off a lot of heat, but not enough to burn metal. Okay. Now it was thought that when the atoms got together, that their respective radius would be, when they got together to form a molecule, a compound of some sort, that bond length, that bond between the 2 atoms that come together would be the sum of their respective radius. For example, hydrogen atom has a bond radius of, not a bond radius, but a radius of 0.037 nm. N stands for the prefix nano, nanometers. It's extremely tiny. When you're talking about nanometers, you're down in the atomic scale. I'm sure you heard about nanobots, okay? Sci-fi stuff, okay, we're down in the atomic scale. Well, anyway, a hydrogen atom has a radius of about 0.037 nanometers. The chlorine atom itself has its respective radius of 0.099 nanometers. So it was thought that when these two combined to form this molecule of HCl, that their sum of the radii would end up to be 0.136 nanometers. Okay, that was the thought. Turns out it's not the case, that the bond length and measuring the actual compound, the molecule of HCl, was actually much shorter. It was 0.127, much shorter than the sum of the 2 individual radii. And what is happening is that when these 2 atoms come together, they have an area of overlap. They're not coming together like the tips of my fingers are represented here, but they actually come together and overlap and share those 2 electrons. There's 2 electrons being shared between the hydrogen and the chlorine. In this case, it's called chloride now, remember, chloride. They're being shared. In fact, because of the electronegativity, remember electronegativity? That is the ability of a bonded element to pull electrons onto itself. Chlorine, or in this case chloride, is bonded to hydrogen. Hydrogen has lesser electronegativity than the chloride atom. Therefore, the chloride atom is pulling the electron density onto itself, okay? Essentially creating what we call a dipole, a area where you have a partial negative and the area that has a partial positive. So that property has a lot to do, that ability to form a dipole has a lot to do with the properties of that molecule, such as solubility, such as boiling point, such as other things that we're going to talk about. So it's all tying back to the dipole bond. All right. So that's what the thought, that's what actually happens when we get two atoms to form a covalent bond. It's not the sum of the radius of the individual atoms, but is much less because of the overlap in the bond that they create. So very quickly, a few things about energy with respect to bond forming and bond breaking, okay? Because energy is required. Energy is necessary to break or to form a bond. Now, anytime you break a bond, that requires energy, okay? That makes sense. You got a bond that's formed, I need to break it up. I got to put energy into the system to break it up. And what happens is it takes that energy, if it's a spontaneous reaction, it takes that energy from the environment. It's absorbed from the environment. The result is it gets cold. That reaction gets cold. We call that an endothermic reaction, an endothermic process. You may be familiar with this. If you go to the pharmacy, for example, CVS or Walgreens, and you buy a cold pack, okay, you got a little plastic bag here, you take it, you smack it because it breaks up the chemicals inside a solution, and that little pack gets cold. It's an endothermic. And that is because there's bond breaking going on in there, which makes this process an endothermic and gets cold. And now you got a cold pack that you can put in your arm or so forth. Now, the fact that it's a reactant means we put it in front of the arrow of, recall I did talk about this reaction arrow or process arrow right here. Okay, this could be, this is an arrow we use in chemistry to describe either a chemical process or a physical process. Now, to the left of the arrow are the reactants, and to the right of the arrow are the products. So heat is required to break that bond of HCl. Therefore, heat is on the reactant side. Okay, it's required for this process to occur. When we actually form a bond, it releases energy. And by releasing energy, guess what? It gets warm. We call that an exothermic reaction. There are also some hot packs you can buy, which are some chemicals that you take the container and smack it, break it, and they react. And by that reaction being an exothermic reaction, it gives off heat. So now you got a hot pack. All right. What's happening there, we're getting bonds are being formed. Okay. In this scenario, when you get bonds forming, energy / heat is a product. So we put heat, energy on the product side of the arrow. Okay. So in this case, we got the hydrogen atom and the chloride atom combining to make HCl, and it gives off heat. The converse of that would be on top, where we take HCl and we break that bond. We require energy, okay, to break that bond, and it gets cold. It's endothermic. Okay. All right. So let's take a look at this true or false questions concerning this molecule here, which is dihydrogen sulfide. Okay. Now it's asking you the question, are electrons shared in H2S? Well, we have to first determine whether H2S is either an ionic compound or a covalent compound. And we identified the hydrogen and the sulfur, and they're both nonmetals. Both being nonmetals, therefore they create a covalent bond. Therefore, Yes, electrons are shared in this particular compound. Now, if the question was, I'm going to write it here to the right, was sodium superscript 2, oh, superscript 2, I don't have the superscript function, but that's 2 sodium and 1 sulfide. We have, that is called sodium sulfide, okay? If we analyze that, we got sodium, which is a metal, sulfide, which is a nonmetal, we have an ionic compound. And so for question number 1, are electrons shared for sodium sulfide? The answer would be false. Okay. All right. Second question. The bond between H and S is ionic. Well, no, it's not, because we just identified hydrogen and sulfur are both nonmetals. They're covalent. So that'll be a false statement, but that would be a true statement for sodium sulfide, right? Because sodium sulfide is ionic. Now, the bond length, the hydrogen sulfur bond length is less than the sum of the 2 ionic radii, okay? And that would be a true statement. Why? Because in the covalent bond, there's overlap, like we just discussed earlier, between a hydrogen and chloride atom. There's overlap to form that covalent bond. However, if this was sodium sulfide, that would be false, right? Because they just attract each other. Now, breaking the HS bond releases energy. Okay. Question is true or false? That would be false. Remember, if to break a bond, it requires energy. To form a bond, it releases energy. Okay. All right. Oh, up here for a second. So this brings us to what is called Lewistow structures. That we're going to take this and we're going to build on this to actually look at the compounds that we're going to be looking at to actually figure out the structure and how things are put together. So that means that if you haven't done so yet, that make sure you do print out your shapes table, okay? Because we're going to be using that quite extensively. Remember the shapes table? If not, let me quickly rehash. We have 2 columns here. We got the general formula column right there. And then from there, in the next column is the geometry, gives you a shape of that general formula. Then we got a name for that shape. And then we have what's called the bond angle, and that's between the things that are bonded to the central atom. The general formula we're going to get from the Lewistow structures that we're going to put together. A represents the central atom, okay? You always know who the central atom is. B, the letter B, I'm talking about the general formula ABE. B represents what is bonded to the central atom. Okay, and they could be the same atom, same type of atom, or different ones. Makes no difference. But it just it's a count of how many are bonded to the central atom. And then E represents how many lone pairs are bonded are on the central atom. Now, there's a difference. We have bonded pair and we have lone pair. Now, if we take the bottom example, the AB2E2, we have 8 electrons around the central atom. 2 of them are bonded. That one and that one, represented by the line. There's 2 electrons in each one. But there's also a pair, 2 pairs specifically, that are not bonded to anything. They're sitting on the central atom. There's 8 of them right there, 8 electrons. So we have, 4 of them not bonded, and they're denoted by these 2 dots. Now that little kind of half oval shape, that's just kind of represents a orbital. Okay, it doesn't really mean anything. It's just to show you the space that these electrons are there. So there's 4 electrons that are not bonded and 4 that are bonded. Those that are not bonded are called lone pair, and they have a big effect on the structure of the molecule. Okay, but more on that as we speak. So E represents how many electrons are non-bonded, how many pairs of those are on the central atom. Okay. But first let's talk about the atoms themselves and how do we draw the Lewistow structure. Very straightforward, okay? We're going to be talking only about those elements, the A elements, group Roman numeral 1A all the way to 8A. Only those are the ones that we can actually determine 100% of the time how many valence electrons they have. The B electrons, the ones inside the transition metals, the inner transition metals, we cannot do that same type of prediction, but only for the A transition metal. Now, we identify the number of valence electrons, and we identify what group they're in, because what group they're in tells us the number of valence electrons. We take the symbol, we write it down, and we treat that symbol like a square, 4 sides, right? And so we start putting the dot around, we start whatever area you want to start around that symbol for that element, put a dot and just work your way around each side singly until you go 4 dots. And then if you need 5 dots, you just start doubling up until you go all the way around. So for example, if you take potassium, oxygen, silicon, magnesium, and iodide, the question may ask, what is the Lewistow structure for these atoms? Well, you simply go find them on the periodic table. And we see the potassium is in group 1A, so they have only 1 valence electron. We can just write a single dot for potassium. That represents the valence electron. Lewistow structures have nothing to do with the core electrons. All they have to do with is the valence electron. Oxygen is in group 6. There should be 6 valence electrons around it. Silicon's in group 4. Notice there's 4 of them around. You know, like if you treat the element like a box, you got 1 dot at each edge of the box. And then if you're going to go more than 1 dot after that, dot number 5, you just start doubling up like we got in oxygen and we got in iodine. Magnesium is a level, a group 2A, 2 valence electrons, hence we got 2 dots to represent the Lewistow structure for magnesium, so on and so forth. So only, again, I repeat, only for the A metals that you can do this for. All right, which brings us to, that was the atoms. Now we're going to talk about the structures, okay? And the way we do this is we look at all the atoms in that structure. You'll be told which one is the central atom, okay? Then we identify all the atoms attached to the central atom, and we count the number of valence electrons that all the atoms bring to the compound. And then that tells us the total number of valence electrons we have to work with, okay? All right, so you'll be told which is the valence electron because it's either going to be in bold or be underlined. If it's not, obviously, I'll let you know which one it is. All right, and 2 things to remember about this whole system. One is the Duet Rule and the Octet Rule. Hydrogen and helium, their rule is a duet. Now, you won't find a lot of bonds with helium. So this really pertains to hydrogen. Hydrogen can only have 2 electrons around the atom, okay, because of its Duet rule. That means that hydrogens will only have 1 bond, and that 1 bond will be attached to the central atom, okay? We can't put more electrons around the hydrogen because there's no room for them. Hydrogen can only handle 2 electrons around it. Keep in mind that some of these electrons will be shared with other atoms, or they're going to be a standalone non-bonding pair of electrons. Those electrons that are shared can be counted toward each atom because they're sharing it. So if hydrogen has 2 electrons around it, whoever it's bonded to is also sharing those 2 electrons. So we can count 2 for the other atom that hydrogen is bonded to. I'll get some examples here. Okay. Now, once we do all that, we identify, oh, hold on one second. We identify the electrons that are bonded, okay? And then the electrons that are not bonded, the non-bonding pair, the unshared. Why? Because we're going to be able to, from that information, determine the general formula. And from the general formula, we go to the shapes table. And from the shapes table, it would tell us the structure and the geometry for that molecule, okay? Now, as I stated, you're going to have only an X amount of valence electrons. You can't put more electrons arbitrarily into the system. If you have a total of 8 valence electrons, that is what you calculated. That is what you got to work with. I can't just arbitrarily either put in 2 more or take out 2. You got 8, you got to work with the 8. If you don't have enough electrons to make sure that everybody's octet is fulfilled, that is where we start creating double bonds and or triple bonds, okay? Because there may be a pair of electrons on one atom that we can share and make a double bond with another atom. And now that one is sharing, that 2 electrons are being shared between those 2 atoms. And we have an example of that we're going to go over, okay? So let's take, for example, water, okay? Now, oxygen is the central atom. And normally 9 times out of 10, the central atom is written first, but there's a few exceptions here and there. One of them is this, where the hydrogens are written first, followed by the central atom, okay? What we do is we add up the total number of valence electrons that every atom brings to the molecule. So we have 2 hydrogens, okay? The hydrogens, each one bring 1 valence electron. So we got 2 times 1, okay? 2 because there's 2 hydrogens, plus 6. That is the number of valence electrons that oxygen brings in. Why? Because it's in group 6. We know that by finding it on the group number, it tells us how many valence electrons it has. Hydrogen's in group 1, brings in 1 valence electron. So we do the math, we have a total of 8 valence electrons to work with. 8. Now, I can do 1 or 2 things here. I can keep it at 8, or what I like to do, when I get my total valence electrons, I should always end up with a number divisible by 2. So now I can take that 8 and divide it by 2. Guess what? I got 4 pair. I like that because for me, I just draw a line that represents a pair, okay? So I got 8 valence electrons, or 8 dots, or I got 4 lines, okay? Now here's where you check your math, because your number should always be divisible by 2 as far as the valence electrons. If you end up with an odd number like 7 or 9 or some number like that, then you know what? You probably took the wrong number for valence electrons, okay? All right. So I got 8 pair to work with, and that's it. That's the pair you got. You cannot add more. You cannot just pull them out. Those are 8 electrons that you're working with for a pair. All right, because the high oxygen is a central atom, I can very quickly draw the first example, my first drawing. And I'm going to use my text here because you can do it quick, and I'll bring my pad here in a second. I can very quickly draw hydrogen, a line, oxygen, a line, and my other hydrogen. Okay. All right. And so I very quickly, by doing that, I've taken care of 2 pair, have I not? Okay, I've taken care of 2 pair. Now, I got 2 pair to use. I start off with 4 pair. I took care of 2 pair because my original structure I put together took care of 2. I got two pair to work with. I got to put them someplace. Now, I can't put them on the hydrogen. Why? Because if I put another pair on each hydrogen, I violate the Duet for hydrogen. Hydrogen right now is already happy, if you will. It's got two electrons around it. It is sharing those two electrons with the oxygen, denoted by the two hyphens. So the only place I have left to put those two pair have to be on the oxygen. So I very quickly just draw a line on the oxygens. Okay. As so. And now I still can't keep track of your valence electrons. I have 4 pair. Okay. 2 of those pairs are bonded with hydrogen and oxygen, and 2 of those pairs are not bonded to anything. Okay. Yes. I don't know why my font here, I got like a 20 font every time in my chat. I need to figure out why. But my fonts are humongous here. Yes, so the question is, are those considered to be lone pair? And the answer is yes. Let me color, different color here. These 2 lines, that one and that one, are the lone pair, okay? Because they're not bonded or being shared with nobody. They're simply straightforward on the oxygen. The line denoted by the hyphens between the oxygen and the hydrogen, those are bonded. Okay. Each hydrogen, I got 2 bonds with hydrogen. I got 2 bonded pair and 2 lone pair. So now my general formula is this. A always will be there. That's my general formula. All right, that represents the central atom. Okay. B represents the number of other atoms attached to the central atom. They could be the same or they could be different. In this case, for water, they're both the same. So it's simply a subscript 2. Doesn't make any difference. Oh, that's a subscript 2. Okay. Now, in this case, E represents the lone pair on the central atom. And yes, we do. We have lone pair on the central atom. Specifically, we have 2 of them. Okay. So that is the general formula. General formula. That's not the formula. That is the general formula for the molecule which we just put together. Okay. AB2E2. Now go back and double check, make sure you still have 8 valence electrons or 4 pair. Sure, I do. I got 4 lines there. That means my valence electrons are correct. And my mathematics is correct. I can continue. So now I go back to the shapes table and I look for A, B, 2, E2. Guess what? Okay. Somebody has their mic on. You may want to, I'm getting feedback. You might want to take your mic to mute it. And so the general formula that we just came up with is AB2E2, and there it is. The molecular geometry shape is right there, and there's 2 lone pair denoted by the 2 dots on the central atom, and the name of that shape is called bent, okay? And that bond angle between the hydrogens for water, that bond angle denoted there is less than right there. That's the bond angle between the 2 hydrogens is less than 109 degrees. Now, what does that mean? Normally, the most common shape that compounds have is called this tetrahedral, where you have 4 entities bonded around the central atom. We call that tetrahedral. That bond angle is by default, the most common bond angle is 109.5. Okay. Now, the reason it's 109.5 because remember, at the bond, there's electrons, 2 electrons there, as I denoted by my arrow. There's 4 pair around it. So these electrons are negative, so they're going to repel each other such that they're as far away from each other as possible. And that is the configuration where those bonded pair are away from each other with maximum distance away, tetrahedral. Now, what happens is if you take out 2 of those spheres, you end up with a lone pair like we just did. And so we have 2 lone pair down here, right there and right there, but they're not bonded to anything. Because they're lone pair, they occupy a lot more space than if they were bonded, like the tetrahedral. But because they're not bonded, they take up more space. And the result is that bond angle that you would think to be 109.5 is much less. That's what the symbol, much less than 109.5. That has a big effect on the property of the molecule. Because of this, water is extremely what we call polar. We have 2 types of polarity. We have nonpolar and polar. And you're familiar with this. If you like Italian dressing, you got a perfect example of a polar solution and a nonpolar solution. Italian dressing has 2 layers. You got an oil layer and a water layer. The water is polar, the oil layer is nonpolar. Because of their differences, they do not mix. Okay. The lone pair here makes that water very polar and therefore changes the properties overall. But more on that as we get more comfortable with writing structures and so forth. And can you repeat which atoms with work? Matt, I don't follow. Oh, which atoms will work with the Lewistow structure? Yeah, we're going to do some more examples. This is just the very first example to get you an idea of what we're doing and how we're going to start making Lewistow structures. In fact, the next page, we're going to jump into some more. Okay. All right. So that's for water. Let's go. Okay. Let's go. Yeah. We're not going to do just one and you just say, hope for the best. No, we're going to be very specific and get you more examples. All right. Let's go back to where we were with water. Okay. And so this is a summary of what we just talked about. Okay. And we end up with a structure for water. Here's the lone pairs on the central atom. 2 of them, 2 lone pairs. And then we got 2 bonded pair, which is hydrogen and oxygen. Okay. We check the octet. Notice that hydrogen. And here's the thing that sometimes people have a challenge with. If we look at this right here, that bond, okay, there's 2 electrons in that line, okay? Those 2 electrons are being shared with the hydrogen and with the oxygen. Those 2 guys are sharing those 2 electrons. Therefore, you can count them as 2 toward the oxygen or 2 toward the hydrogen. So if we just look at hydrogen by itself, just look at hydrogen all by itself, there's 2 electrons on hydrogen, which fulfills a duet for hydrogen. The same is true for the other hydrogen, okay? Now, when we look at the oxygen, we can see that we have 2 electrons that are now bonded, 2 that are shared. So just looking at the oxygen by itself and counting all the electrons around it, guess what? You have 8 electrons, which fulfills the octet for oxygen. Of those 8 electrons, 4 of them are shared with another atom, okay? Hence the covalent bond. Right. All right, here we go. Let's try some examples here, okay? Now, we have HCN very nasty, poisonous gas. Okay, first thing we got to do is create our grocery list of valence electrons. Okay, so we have hydrogen, and we know there's one hydrogen, and it brings one valence electron to the table, if you will. Okay, one hydrogen, one valence electron. Also notice there's an underscore on carbon. That tells you that carbon is a central atom, and the nitrogen and the oxygen are bonded to the central atom. Okay, so next thing, carbon. All we're dealing with is the valence electrons. Remember, we don't care about the total electrons, just the valence electrons. So carbon, there's one carbon. Okay, one carbon. But what group is it in? It's in group 4, right? Because it has 4 valence electrons. And so the number of valence electrons that carbon brings in is 4. Okay. And like I said, we're going to make our grocery list of all the valence electrons. Let's take a look at nitrogen. Nitrogen, we have one nitrogen based on the formula that we're given. Okay. We need to know how many valence electrons nitrogen brings in. And we find it on the periodic table. It is in group 5A. That tells you there are 5 valence electrons. Okay. So our total will be what? Total valence electrons. What do we have? 5 plus 4 plus 1. What do we got, guys? 10 valence electrons, or guess what? 5 pair, right? Because it's divisible by 2. Exactly. We got 5 pair. So that's what you got to work with. You can't subtract. You can't add any more because you don't have the other atoms. That is what you got to work with. And that's how we're going to put it together. Okay. So we got 5 pair to work with. So now what I'm going to do is I'm going to bring in my board and start drawing something. All right. We had carbon. Let me change the color here. We had carbon, and then we can very quickly, okay, we can very quickly write carbon and then bond hydrogen and bond nitrogen through that. Okay, because we were told there was HC. Oh, hold on. Yeah, we were told HCN, and we had underscore into carbon. Okay, excuse my pen here doesn't not working quite well. Okay, so I can very quickly down here type in hydrogen bonded to carbon bonded to nitrogen, because carbon is my central atom, and I can just quickly add the other atoms that are attached to it. Guess what? How many? We started off with 5 valence electrons, right? We just used 2 right now. We got 3 pair. We're not 5 valence, 5 pair. We have 5 pair to work with. We just calculated. I used 2 right now to bond the hydrogen and nitrogen. I got 3 left. Okay. I can put them anywhere I want, except I can't put them on hydrogen, right? Because hydrogen is happy now. Hydrogen has 2 around it. So I can either put them on the nitrogen like that. Okay. And maybe I ought to maybe I ought to do this just to make sure we keep everything straight here. I already put 2 in there, so I'm going to add now my other one there, one there, one there. Do I not still have 5 pair? I got 3 in the red because that was left over. Okay. That was left over from there. And then 2 in the red because that's what I was told in the beginning I was bonded. So now, do I still have 5 pair? Yes, I do. So I'm good with that. Now, once we do that, I'm still got 5 pair. You got to keep track of that. And every time you write a structure, make sure you double check to make sure you still continue with the right number of electrons you started off with. Hydrogen is happy, so I don't have to do anything in hydrogen. Okay. Now, if I look at nitrogen, I got 2, 4, 6, 8 electrons around nitrogen. So it's happy as it stands. So nitrogen's okay the way you wrote it. Hydrogen's got 2, so it's okay too. Problem is carbon. Carbon only has a total of 4. 2 there, 4. So it's shy the octet. So what needs to be done is I need to take some of these electrons, that one, for example, and that one, and make a double bond and maybe even a triple bond. It looks like I'm going to make a triple bond. And so what I end up with is hydrogen bonded to nitrogen. Okay. Now check my lines. I still have 5 pair. I didn't lose anywhere along the lines. I got 1 pair on the carbon hydrogen, and then I got 4 pair around the carbon. 3 are shared with nitrogen, 1 is shared with the hydrogen. And then nitrogen also has 4 pair. 3 are shared with carbon, and then there's 1 on nitrogen itself. Okay, so I come up with that particular formula. The general formula I come up with would be A, B, 2. Let me write this over here. A, B, 2. A represents carbon. B represents 2 things bonded to the central atom, which is nitrogen and hydrogen. There are no lone pair on carbon. All of them are bonded, so there's no E here. Okay, no E. Okay, so my general formula is AB2. And I go to my shapes table, look for AB2. It is the first entry there, right here, AB2. You can see here, the central atom could be carbon. The one on the left is hydrogen. The one on the right is nitrogen, or vice versa. That bond angle is 180 degrees between the hydrogen and the nitrogen. And the shape is called linear. Okay? Linear. And let's see what we come up with. There's the same structure we just wrote. Okay? The octet is fulfilled on the carbon and the nitrogen, and the duet is okay with the hydrogen. Okay? We still have 5 pair. Isn't that what we calculated? 5 pair total. There's 5 pair electrons sitting there. Okay. All right. Let's do the next one. Carbon. That one is carbon, hydrogen, and fluorine. These are what we call carbonated or halogenated hydrocarbons. The next one. So same setup. We do our grocery list, okay? And so we got carbon, We got one carbon, and it is in group 4. So it has 4 valence electrons, right? Okay. Hydrogen, same scenario. We got one hydrogen. It brings in 1 valence electron. So we got 1 valence electron from the hydrogen, 4 from the carbon, 4 from the hydrogen. All right. Now we got the fluorides. All right. We got 3 fluorides. Now, how many valence electrons does each fluoride bring in? Anybody know? How many valence electrons does fluoride have? What do we got? Exactly 7. It is in group 7. Okay. So there's 7. So we got a total of 21 valence electrons from the fluoride. 21. So what do we have total wise? $26. Exactly. We got 26. Whoop, 26 valence electrons, or guess what? 13 pair, right? 26 divided by 2 is 13 pair. Okay. All right. So now, going back to the formula you're given, carbon has the underscore, which means that's a central atom, which tells you that the hydrogen and the fluorides are all bonded around that. Now, so I'm going to now take the my pad here. Let's go here. Let's clear up this mess there. All right. And so we had carbon, and we had the hydrogen bonded to there, and then the fluoride, another fluoride. I can very quickly write that. Okay. And so we had 13 pair to work with. I just took care of 4. Doesn't that leave 9 pair from the original 13? I just took care of 4, right? Yes, correct. And so I'm going to change the other color of that so we can see. So now I can't put it on the hydrogen. I got 9 pair. Now I can't put it in the hydrogen because the hydrogen's full. And guess what? I can't put it on the carbon either. Why? Because there's 8 around carbon already. So where's the only logical place that they must go? It's got to be on the fluoride, right? Exactly. Yeah, go on the fluoride. They got no place else to go. And so let me see if I can get my reference point here. And so there's 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go, 9 pair. All right. And then I got the 4 inside. Guess what? 13 pair. All right. Which is what we started off to begin with. What about my general formula? Well, let's figure this out. I got A, B, 4, my general formula, AB4, because there's no lone pair on the central atom. All we care about is lone pair in the central atom. Right now, there's 4 bonds, 1 hydrogen, 4 fluorides. Each fluoride has 1 bonded pair and 3 unbonded pair. Okay. Now, here's a question. Tetrahedral, exactly. So if you take that general formula, AB4, okay, and you go to the shapes table, Look for AB4. There it is. There's a general shape right there. We got the central carbon, one hydrogen, and the 3 fluorides around it. That shape is called tetrahedral, and that bond angle is 109.5. Okay, 109.5. All right. And so now we go back. Let's see what we get over here. How we got the general formula, Madison, you asked? Yeah. Well, going back to, let me go back to the whiteboard. Okay. Okay, remember, we have the general formula that we utilize is, crazy thing here, is A, B, X, E, X, okay? That's a general formula. A is always the central atom, okay? B is whatever's bonded to the central atom, and E represents the lone pairs, if there's any, in the central atom, okay? Now, X can vary in number. At the minimum is 2. You'll see we just did AB2 earlier, the linear one, where we had the HCM. So at the minimum, it could be a 2, and at the maximum, it can be a 4, okay? The E at the minimum can be a 1, and at the maximum can be a 2 lone pairs, or yeah, on the central atom. Okay, so if we look at the formula we just came up with, we see that carbon has bonded to it 1, 2, 3, and 4. 4 atoms are bonded to the central atom. So our B becomes 4. The X is 4. There's no E here, okay? And why wouldn't it be an E? Think about this for a second. Let's say, for example, we put a lone pair there, okay? By mistake. Well, look, now we violated the octet. We got 2, 4, 6, 8, and valence electrons, 10 electrons around the carbon. That would be a violation of the octet rule. So that couldn't be the case, right? So we got to do that. And the same is true for hydrogen. If we added more atoms or electrons to hydrogen, that will violate its Duet rule. So this would be 2, and this would be 2. That's 4. So that would be a violation. So at the most, hydrogen can only have 2 electrons, right? So that means that our general formula would be AB4. Okay? Did that help you, Madison? That's how we come up with a general formula that we utilize in the shapes table. Okay, no problem. So then we go back to the slide for that. And guess what? We came up with the same formula. Okay. These are nasty compounds. These were used a lot in propellants and so forth. And these chemicals go up to the upper atmosphere and react with the UV light. These also, the chlorides, the ones that have chloride in them, they're halogenated hydrocarbons that go up to the upper atmosphere and react with UV light and create compounds that react with the ozone. Now, there's 2 types of ozone. We got the bad ozone and the good ozone. The bad ozone is what we breathe here, and our environment's not the best. We got a lot of junk and stuff going on from the exhaust of vehicles, and the ozone goes up, and that can destroy tissue in our lung and so forth. But the good ozone is way up in the sky. It's a very thin layer. And what that does, it protects us from the UV light. And what's happened, these hydrocarbons, halogenated hydrocarbons, have gone up there and destroyed our ozone layer. So we got some big giant holes in our ozone layer, which means more UV light coming into the earth. which means if you use that protective for the sunblock, you'll see numbers that are what, 40, 50, 60, 70, the block numbers. That's when I was a kid, they were probably down in the 10s, 20s, but now there's so much UV lights out there causes problems. All right, so that's a side note on these guys. This is the third one, carbon dioxide. Very interesting example here, okay? So same scenario. We'll do this one and we'll call it a day. We got to do a grocery list first, okay? Carbon dioxide. So we got carbon, okay, one carbon, and let's do this correctly here. One carbon times 4 equals 4 valence electrons, okay? Oxygen, okay, we have 2 of them. Now, how many valence electrons does oxygen bring to the table here? Each one, how many valence electrons? 4. Are you sure? 6. Yep. Okay, oxygen is in group 6, so it has 6 valence. Excuse me, 6 valence electrons. Okay, so that means that it brings to the table 12 because there's 2 of them. Okay, so our total will be what? 16. We got here, we got 16. Yep, we got 16 or 16 valence electrons or 8 pair. Okay, or 8 pair. Now, we got 8 pair carbon dioxide. Carbon is the central atom, and oxygen is bond. Those 2 oxygens are bonded to the central atom. All right, and we got 8 pair to work with. And so let's pull up my whiteboard again, and let's clear this guy here. And so we're going to start with carbon, and then oxygen, and then bond it over here, oxygen, right? And we said we had 8 pair minus 2 is a 6 pair to work with left over. Okay. Now, in this case, you can put them anywhere you want. So as long as you don't violate the octet. And what I like to do is I start from the outside atoms and I work my way in. So I'm just going to start with, and I'll make this a different color so we know that. And let's try. Hey, we'll make them pink. How's that? All right. And so these are the ones that are left over. So we got 1, 2, 3, 4, 5, and 6. Okay, I'm gonna put this eraser. I don't want to make that be mistaken. All right. So now make sure I still got 8. Do I still have 8 pair? Sure do. Right. I got 6 pink ones and 2 red ones. That's 8 pair. That's what we calculated with 2 oxygens, 2 carbons. All right. Now check your octet. Around the oxygen, we got 8, each one, in fact. 3 pink ones and 1 red one. Okay, that's 8 on both of them. The carbon is shy. It's shy 4 electrons because there's only 4 of them right now. And so what we got to do is, remember, when you're shy electrons, you just cannot magically just pluck them in from space. You got to work with what you got. And what you do is you borrow from Peter and you give to Paul, if you will. Okay. So we're going to borrow a pair from, say, here and make a double bond, and borrow one from here and make a double bond. what results in this structure. Okay. By making a double bond, borrowing one pair from each oxygen and making a double bond, have we done anything to change the total 8 pair? No, we got 1, 2, 3, 4, 5, 6, 7, 8. We still got 8 pair. Okay, we didn't magically generate more electrons. Now check the octet. Each oxygen still has 8 around it. There's still 8 electrons around each oxygen. 2 of them are non-bonded and 2 of them are bonded. Okay, and then look at the carbon. There are 8 pair around carbon as double bond pairs. Okay, the octet is happy for everybody. What general formula do we get? Well, A, we always get A, and then B, there's only 2 things bonded around carbon. So our general formula would be AB2. Okay, we go to the shapes table, AB2, very first entry. Okay, that's the shape there. The 2 oxygens, there's a bond angle of 180 degrees. Its shape is linear. All right, and it's linear. That's correct. All right, and so from there, let's go see what it comes up. Okay. All right. I will stop it here, but you can look very quickly with the next one. The next one's called ammonia, Nh3. Next time you clean a window with ammonia cleanser, that's what you're smelling, Nh3. Okay. Nitrogen is in group 5, right? Group 5. There's 3 hydrogens. So we got 8 valence electrons to work with, or 4 pair. Nitrogen is the center pair. We can very quickly let me clear that. You know, we write nitrogen here. We got hydrogen sitting there, hydrogen right there, hydrogen right there. We have 2, 3, 6, and then our lone pair goes on the nitrogen. So we still have 8 pair there, right? 5 valence electrons from the nitrogen, 3 from the hydrogens is 8. So we still got 8 pair. We couldn't put that single pair on the hydrogen because the hydrogens are happy. Okay, the duet's full. And so here, the only place that last pair has to go is on the central atom. Okay, nitrogen, which means that our general formula is A, B, 3, E. E because there is a lone pair on the central atom. Okay. B3 because there's 3 hydrogens around the central atom of nitrogen. And so we can go look that up. AB3 right here. And that's the shape. See that lone pair in the central atom denoted by the 2 dots? So its particular shape is trigonopyramid. And that bond angle again would be less than 109, simply because those lone pair occupy more space, shoving those hydrogens down a little bit and decreasing that angle. The other thing too is we just demonstrated this. There's a lone pair on that central atom. We have a polar species, a polar compound. Okay, because of this lone pair. And that'll become a lot clearer here in a bit. So from here, and the last one right there. Okay. All right. So let me stop it here. We didn't get too far, but that's okay because it takes time. We have to go through some examples on how to write the structure because this is going to tell us as we go down the road when we write the formula whether something is polar or nonpolar, okay? Which would tell us whether it be soluble in water or in oil, and which would tell us more properties. Would it be have certain properties in that it will have higher boiling point than compare with another molecule or less boiling point. It's all eventually, hopefully, will come together. But remember, at this time, what we did is we started with atoms. We talked about the atoms. Those are the alphabets of our new language, if you will. And we made ions, and then we talked about putting these ions together to make compounds. And then we're going to put all these compounds, like two types of compounds, ionic compounds and molecular compounds. And then we just build up on that. Okay. All right. So let me stop here.